Today we are going to learn about mastering duality and convex optimization. We will explore how duality simplifies complex optimization problems, how to formulate dual problems, and identify optimal solutions efficiently. By the end of this video, you'll be equipped with the skills to apply duality in real-world scenarios. Welcome to this comprehensive guide on mastering duality and convex optimization. In the realm of optimization, duality offers a powerful framework to simplify and solve complex problems efficiently. At its core, duality involves formulating a dual problem from a given primal problem, providing insights into the structure and solutions of the problem. Throughout this video, we will delve into the fundamental principles of duality, explore the differences between primal and dual problems, and understand how duality can be applied in various real-world scenarios to achieve optimal solutions efficiently. Let's embark on this journey to master duality and convex optimization. In optimization, the concept of primal and dual problems forms the crux of duality theory. The primal problem is the original problem we aim to solve, typically involving the minimization or maximization of a certain objective function subject to constraints. The dual problem, on the other hand, is derived from the primal problem and often provides a lower or upper bound to the optimal value of the primal problem. Understanding the relationship between these two problems is crucial as they offer different perspectives on the same underlying problem. The solutions to the dual problem can provide insights or even direct solutions to the primal problem, making duality a powerful tool in optimization. By formulating the dual problem, we can often simplify the problem-solving process, leverage computational advantages, and gain deeper insights into the problem structure. Let's explore how to formulate dual problems from primal ones and the advantages this brings to the table.
Duality theory encompasses two fundamental concepts, weak duality and strong duality. Weak duality states that the value of the dual problem provides a bound to the value of the primal problem. Specifically, in the case of minimization, the value of the dual problem is always less than or equal to the value of the primal problem. This concept is universal and holds for any primal dual pair. Strong duality, however, takes this a step further. It states that under certain conditions, known as constraint qualifications, the optimal values of the primal and dual problems are equal. This means that solving the dual problem can directly lead to the solution of the primal problem. Understanding these concepts is crucial as they determine the relationship between the primal and dual solutions and help in identifying optimal solutions efficiently. Let's delve deeper into these duality theorems and explore examples that illustrate their practical implications.
Duality finds applications in various real-world optimization problems, making it a valuable tool across multiple domains. In economics, duality is used to analyze consumer behavior and production efficiency, providing insights into cost minimization and utility maximization. In machine learning, duality plays a crucial role in solving large-scale optimization problems efficiently, particularly in support vector machines where the dual problem is often easier to solve. Network optimization is another area where duality simplifies complex problems like maximizing flow in networks or minimizing congestion. By leveraging duality, we can break down these problems into simpler subproblems that are computationally more manageable. The advantages of duality extend beyond simplified computations. They provide deeper insights into problem structures, allowing for more informed decision-making and efficient resource allocation. Let's explore some real-world scenarios where duality has been effectively applied to solve complex optimization challenges.
Formulating a dual problem from a primal problem is a systematic process that involves several key steps. The most common approach to derive a dual problem is through Lagrangian duality, where we introduce Lagrange multipliers to the primal constraints, forming the Lagrangian function. The dual function is then derived by minimizing the Lagrangian with respect to the primal variables. This process leads to the dual problem, which is typically a maximization problem if the primal is a minimization problem. One crucial aspect to consider during this process is the presence of Slater's condition, which ensures strong duality holds, allowing the primal and dual optimal values to be equal. While formulating dual problems, practitioners should be mindful of common pitfalls such as incorrectly setting up the Lagrangian or missing constraint qualifications. Let's dive into detailed examples that illustrate the step-by-step process of formulating dual problems, highlighting the nuances and potential challenges one might encounter. Understanding the geometric interpretation of duality can provide profound insights into the nature of optimization problems. Geometrically, the primal problem can be visualized as finding a point within a convex set that minimizes, or maximizes, a certain objective function. The dual problem, on the other hand, can be visualized in terms of hyperplanes and supporting planes that represent the constraints of the primal problem. The intersection of these hyperplanes forms a feasible region where the dual problem operates. This geometric perspective highlights the relationship between primal feasibility, dual feasibility, and optimality. The dual problem essentially seeks the tightest bound provided by these hyperplanes, thereby offering an alternative yet equivalent view of the optimization problem. By visualizing these concepts, one can gain a clearer understanding of how duality simplifies and solves complex problems. Let's explore some examples that illustrate these geometric interpretations, emphasizing how they aid in comprehending duality more intuitively. Duality not only provides a framework for formulating problems but also serves as a powerful tool for identifying optimal solutions. One of the key methods to achieve this is through the principle of complementary slackness, which provides conditions that must be satisfied to get the optimal solutions of both the primal and dual problems. By examining these conditions, we can verify the optimality of a solution and gain additional insights into the problem's structure. Duality also enhances computational efficiency by allowing us to solve the dual problem, which may be simpler or require fewer resources than the primal. This is particularly beneficial in large-scale optimization problems where direct approaches might be computationally prohibitive. Let's explore how duality facilitates the identification of optimal solutions, with examples that demonstrate the practical application of these principles in various optimization scenarios.
While duality is a powerful tool in optimization, there are several common pitfalls that practitioners should be wary of. One of the most frequent mistakes is the misinterpretation of duality. Assuming strong duality holds without verifying the necessary conditions can lead to incorrect conclusions. Incorrect formulation of dual problems, such as errors in setting up the Lagrangian or neglecting specific constraints, can also lead to misleading results. Additionally, neglecting constraint qualifications like Slater's condition can result in the failure of strong duality, undermining the equivalence of primal and dual optimal values. Over-reliance on dual solutions without cross-verifying with primal solutions can also pose risks. To avoid these pitfalls, it's crucial to thoroughly understand the theoretical underpinnings of duality, carefully formulate dual problems, and verify all necessary conditions. Let's examine some strategies to avoid these common pitfalls and ensure robust application of duality in solving optimization problems. In the field of machine learning, duality plays a significant role in enhancing the efficiency and effectiveness of various algorithms. A prime example is in support vector machines, SVMs, where duality is employed to transform the primal problem into a dual problem that is often easier to solve, especially in high-dimensional spaces. This transformation allows the use of kernel methods to handle nonlinear separations efficiently. Duality also aids in the development of efficient training algorithms by focusing computational resources on the most critical aspects of the problem. In regularization, duality provides insights into the trade-offs between fitting the model to the data and maintaining model complexity. These insights are crucial for developing robust models that generalize well to unseen data. Let's explore some practical examples that highlight the application of duality in machine learning, emphasizing how it contributes to the development of efficient and effective learning algorithms. As we conclude this journey into mastering duality and convex optimization, let's reflect on the key concepts we've covered. We've explored the fundamental principles of duality, the distinctions between primal and dual problems, and the conditions under which strong duality holds. We've also delved into the practical applications of duality in real-world problems, particularly in fields like economics and machine learning. The insights gained from duality not only simplify complex problems but also enhance our understanding and ability to identify optimal solutions efficiently. As you continue your exploration in optimization, I encourage you to apply the principles of duality in your problem-solving endeavors and consider further resources to deepen your understanding. Thank you for joining us, and best of luck in your optimization journey.